So, hi guys. So, how are you all? How are you doing? So, hope everyone is doing great. So, today in yesterday's class, we completed our first chapter, that is electrostatics. We completed the chapter electrostatics. In today's class, we'll be starting with the next chapter, that is capacitance and capacitors. So, this is very interesting chapter. So, whatever we learned in our previous class, so whatever we learned in electrostatics, we are going to apply that directly over here. So we'll be applying those. Okay, we'll be applying those concepts whichever we studied in electrostatics. Most of those concepts would be studied here. Okay, we will be applying that. So tell me, how many of you? Okay, let me launch the technical check poll first. Okay, guys, everyone, please take the technical poll. Um, Everyone who are present here, please take the technical poll. So I will be asking few questions based on once we start this. Yes, yes. So is my technical poll? I mean, I have launched a technical poll. Is it visible, guys? Yes, cool, awesome. So guys, yeah. Once we have posted, and I'll be asking you a few questions on the previous chapter. Okay. So I'll be displaying few questions and I'll be asking few questions again. So you should be in a position to answer. Now let's see. So only one out of three students. Okay, why are very less students here? Please call your friends. Okay, okay. Hi YouTubers, everyone. Good afternoon. So please let me know if my voice is audible clearly and if my screen is visible clearly. Okay, someone have issues in hearing, listening the voice. Is it Santosh? I don't know. Hope my voice is yes, cool. Thank you. Thanks, bro. YouTubers, I hope you guys are able to hear and see me. I mean, see the blackboard and hear my voice clearly. Yes. So we'll wait for more people to turn up to the class. Yes. Cool. Okay, cool, guys. So I hope everyone try to revise about your previous chapter, that is electrostatics. I hope everyone revised that entire chapter once at least. Yes. Any doubts in that? Okay, cool, cool, cool. So in today's class, we'll be starting with electrostatics applications. That is, first, a very first basic thing is capacitance and capacitors. So for this chapter, we require lots of basics from our previous chapter. So one such thing is permittivity. So we should know what is permittivity. Then we should also know about other concepts like the conductance, the modes of charge. From modes of charge transfer, we should know about inductance. So how inductance happens. Then again, we have to know about electric fields. So how electric fields originate or how electric fields are generated. I mean, how electric fields are created, properties of electric fields. Then also we should know about electric potential. What is potential energy? What is electric potential? So these few terms we have to know very well. Okay. So guys, tell me now, the chat box, what type of fields does static charge generate? If we have static charges, what type of fields does that static charge generate? So everyone who are in Zoom and who are in YouTube, please reply in your chat box. There's chat box, right? Please reply in the chat box. So what type of field is available, or what type of field exists when there are only charges present, stationary charges are present? So I don't know why students have taken so long to appear. Yes, what type of fields does exist? So yes, correct, Hari Prasad. Correct, Ramakrishna Reddy. So guys, is there anyone who is not able to see the screen properly, or not able to see the or hear my voice clearly? Yeah, please check your network. Okay, let's start with this. Okay. Yes, guys. So yeah, yes, correct. Pranay, Ramakrishna Reddy, Bhargav, Madhavi, correct. So whenever we have Narendra Modi, why? Why is your name? Is your name really Narendra Modi, or I know from JNVP Japur? Cool. Okay. So guys, yes. So I'm going to end the poll. Hope everyone is able to hear my voice clearly and see the screen clearly. I'm going to end the poll. Yes. Cool. So my first question was, yep. My first question was, what type of fields would generate when we have some charges which are stored or which are static in nature? Say if I have n number of positive charges stored or locked in a ball. Say I have a ball. I have a ball. Inside this ball, I have many positive charges. So what type of field would be generated in this ball or around this ball? Yes, YouTubers had given me the right answer. Any answer from here, guys? The Zoom audience, please give me answer. What type of field would generate due to? Yes, correct, Dhanush. It would be always the outwards. But what is that field? What type of field is generated when we have stationary charges? Yes, correct, Rajwal. So we'll be having electric fields, right? So we had studied this. So this entire thing, which has uniform charge distributed over the entire surface, can be considered as a point charge, single point charge with charge Q, whose which generate electric field in all directions. So when we have stationary charges, we give rise to electric fields, right? So I think I had discussed one more thing. So when these charges start to move, when these charges start to move, moving charges generate which type of field? Moving charges gives which type of field, guys? Come on, tell me. Yes, correct, Dhanush. YouTubers, please try to answer. Try to be active, guys. Come on. So we are going to study the application part of electrostatics here in this chapter. So most of what we have studied in electrostatics would be applied in this practically. So this chapter would be the practical application. So we can say this is a practical approach for this chapter. Yes. So in the very beginning, I had told you the stationary charges would give rise to the electric field. The moving charges will always give rise to magnetic field. Correct, Prajwal? So yes, correct, Ganush. Correct, Madhavi. No, Hari Prasad. It only generates, see, stationary charges, stationary electric field. Moving charges, magnetic field. Now, accelerating charges. So if there is some accelerating charge, it gives electromagnetic fields, okay? EM fields or EM waves. Okay, this basic should be considered till the end of your 12th standard. This is the only basics which we require till the end of your 12th standard, because in all chapters we have the same thing. Okay, if you take even your ray optics also, even there you will be studying that light is a is a type of electromagnetic wave, right? So we will be learning about these charges which are stationary then moving. So next part after this capacitors and current electricity, we'll be dealing with moving charges, where we study about magnetic fields. Then after the magnetic fields, we'll be studying about accelerating charges, where we'll be studying about EM waves. Then we'll be studying about alternating currents. Then we'll be studying about ray optics, wave optics, and finally we'll be studying about communications and also some part of semiconductors and some modern physics. So modern physics is nothing but where the what's that? electron, proton, neutron, bombardment, and all those stuffs. We'll be studying about them, right? So in today's class, we'll be starting with second chapter of your physics, that is capacitance and capacitors. Guys, you see many of these devices. So don't worry if you have not seen. Have you seen this? But yet, my question was, have you seen such devices? I hope all of you might have broken some electronic gadgets by now. By your 12th standard, I hope everyone might have broken some or the other gadgets. Have you seen any such structures inside your circuit board or motherboard? So we'll be studying about all of these. I mean, I'll be introducing all of these, at least one of, I will be studying about these in detail. So if you require in the last 10 minutes, I'll be giving you the practical application of all of these capacitors, different types. Okay. So these are the different types of capacitors. So this, yeah, it will be inside your remote, inside your all electronic toys, also in all your costly equipments. Okay, costly electronic equipments. If you have broken a charger, you will see such structures. If you have broken a FM, your music, right? Yeah, FM device. So if you have opened that radio device, if you open that, even then you would see such structures. So these are nothing but capacitors. Okay, we'll study about them in detail in this chapter. Why capacitors? What are capacitors? How capacitance exists and stuff. So let's start. So before we start, I want you to take a recall test. Guys, everyone, please take recall test. For this, I'm launching you a poll. So this is just for you guys to take a recall of what we have studied from your previous chapter, how much you remember from your previous chapter, how much you remember. Okay, so there are 5 questions. I am displaying first 3 questions. Next, I'll display 2 questions. Please take care. I mean, everyone, please try to answer these questions in series. Say, after first question, answer second question, then third question. So all the Zoom audience, you have been given a poll in which you have 5 questions, 5 sets of questions. I request everyone to answer the 3 questions first. Also, the YouTubers, please try to answer the 3 questions first, then I'll display the other 2. So only submit after you answer all 5 questions. Okay, start. So first question goes like this. Rubbing a body may cause a slight change in its weight due to, yes, yes guys, come on, try to answer with one or more answer, please, everyone. And Zoom audience, please answer in your polls only. Okay. Yes, Pooja. Pooja, are you getting your, I mean, please wait for all displaying all 5 questions, Zoom audience. Pooja, you raised your hands. Any issues? Okay, so guys, come on, answer this. So second question is, an electric dipole is produced, oh sorry, an electric dipole is placed in an electric field generated by a point charge. Then what is the suitable option? Third question, a positive charged particle is released from rest in a uniform electric field. A positively charged particle is released from rest in a uniform electric field. The electric potential energy of the charge, have to reply. Yes, guys, come on, try to answer. Yes. Hope everyone have completed first 3 questions. The third question, yes, a positive charge particle is released from rest in a uniform electric field. The electric potential energy of the charge. Okay, come on, guys. So let's go to the third question. I mean, let's go to the fourth question. Fourth and fifth question. Come on, guys. So I hope everyone have tried to answer first 3 questions. Shall I move to fourth and fifth question? Please reply in the chat box. Shall I go to fourth and fifth question? Shall I display fourth and fifth question? You should be very quick, guys. This should not take more than for 2 minutes. Okay. Yes, come on. Try to answer the fourth and fifth question. If anyone requires first three questions, we'll display that after fourth and fifth question. Okay. Okay. Please don't submit yet, guys. Don't submit yet. Someone had submitted already. Please don't submit. The Zoom audience, please don't submit yet. Once we have completed all 5 questions, only then submit these. So fourth and fifth question have displayed. The flux of the electric field through a closed surface is. So if the flux of the electric field through a closed surface is zero, if the flux of the electric field through a closed surface is zero, then what can you say about that surface? Okay, done. Okay, we'll check all the answers. Okay. Last question, guys. The electric field in a region is directed outward and it's proportional to the distance r from the origin. Taking the electric potential at the origin to be zero, then what can you say? Okay, guys. So once when everyone is ready, please submit your answers. Everyone, once you have submitted, or once you have answered all questions, please submit your polls. Zoom audience, please submit your polls. Everyone in Zoom, please submit your polls. Everyone in YouTube, if possible, it's a request from my side. You could answer all 5 questions at once in your chat box. You could answer all 5 questions, 1, 2, 3, 4, 5, 1, comma answer, 2, comma answer, and 3 answer, 4 answer, 5 answer. Yes, cool. Thank you, Lakshmi. Okay, guys. So this recalls our previous chapter. Okay, entire prerequisite of electrostatics would be thorough with these 5 questions, I guess. So if you want more questions, yep. Anyway, important notice, guys. So you would be having your test on your P15 this weekend. I think I notified yesterday. Yes, thank you, Bhargav. Thank you, Rakesh. Thank you, Priyanka. So everyone in the Zoom, shall I end the poll? Guys, please be quick, be quick. So I received only 11 out of 29 responses. Yes, guys, come on. Please be quick. Okay, I'm going to end the poll, guys. Come on. Okay. So I have received these answers for your poll. So let's check the answer, okay? Let's check the answer for all. So please check your answers. These are the answers for the questions. So first one is option B. Second one is option D. Third one is option C, and fifth one B, and fifth one C. So we'll check each question. Okay, everyone, please check your answers and let me know how many of you got all 5 out of 5. So first question, let's see answer. Okay, so rubbing a body may cause a slight change in its weight due to, yes, first answer is due to charge transfer. So when there is charge transferred from one body to other body, there will be a reduction of weight. How much? Say approximately 9 into 10 power minus 32 kgs would say when one electron is shifted from one body to other body. Yes, when loss of material. Okay, suppose it's very abrupt, Dhanush. Yeah, rubbing a body may cause slight change in its weight due to transfer of charges according to electrostatics. We won't be rubbing very hard, Dhanush. to lose material due to friction. So we won't be rubbing so hard. Okay. So we may lose approximately 9 into 10 power minus 32 kg per electron. For one electron, we may lose this much amount of weight. Okay. So first answer is option B. Now second question. So if we check the second question, an electric dipole is placed in an electric field generated by a point charge. So what could be the most appropriate answer? So the answer given is option D. Okay. The torque on the dipole due to the field may be zero. So electric dipole placed in an electric field generated by a point charge, the electric field on the dipole must be zero. This cannot be zero. Electric field due to dipole cannot be zero, right? The net electric field on the dipole may be zero. Only at the midpoint it is zero, but not everywhere. So this can't be the option. The torque on the dipole due to the field must be zero. No, they did not mention about the theta. So what can be zero? The torque on the dipole due to field may be zero. It may be zero, may not be zero, right? So it may be zero. See, in option C, they had given us must condition. Must condition does not satisfy. Must condition means it must be zero. For sure, it will be zero, but it's not must. It's may. It may be zero, may not be zero, right? So option D suits good here. Next, in next question, a positively charged particle is released from rest in a uniform electric field. The electric potential energy of the charge remains no, increases because the charge is moves along the electric field. So what do we know? The positively charged particle is released from rest in a uniform electric field. The electric potential energy of the charge increases. So in the direction, so when we are trying to move against the direction of electric field, say if I have some electric field in this direction, if I try to move a charge against the direction of electric field, what happens? Sorry, if we move along the direction of electric field, my electric potential energy increases. So this is option B. Next, sorry. Sorry, where is option C and option? Okay. Next, guys, next question. If the flux of the electric field through a closed surface is zero, so what can be the condition, guys? If a flux, so we learned yesterday in Gauss's law, in previous class, we learned that phi is equals to Q enclosed upon epsilon naught, right? So my flux depends only on charge and only on the material medium. So if the flux of the electric field through a closed surface is zero, then what can we say about the condition? When can it be zero? When can my flux be zero? When can my flux be zero? So what are the two conditions? Either my epsilon should be infinity or my Q should be zero, right? Not Q. I mean, the effective charge inside the surface, everywhere on the surface should be zero. So electric field may be zero. So other thing which you know for flux is integral of E dot dA. So if my electric field is zero, everywhere inside the surface, then my flux will also be zero. So this is option B. Next, the electric field in a region is directed outwards and is proportional to the distance r from the origin. Taking the electric potential of the origin to be zero, it is said that it is proportional to r square. Okay, it is proportional to r square. So these are the conditions. These are the answers for the given question. Okay. Potential energy is constant at all points and it is increasing. So we'll check that, Prasad. I think this question, I think there is some error in the question. Guys, excuse me for a minute. Okay, there is no option C and option D. We'll check that answer. Okay, I'll give you the detailed solution, Hari Prasad, later. Okay. Now let's continue. Now, guys, so these were the answers for your questions. So next, we'll come to capacitance. So guys, what do you mean by capacitance? Tell me, what do you mean? So what do you know if I say capacitance, or what is capacity, guys? Capacity andre ಏನು? What is your capacity? What do you mean by capacity, guys? What do you mean by capacity? Or what is generally what do you, when I say capacity or capacitance? Okay, chill, bro. So when I mean by yeah, yes, correct, Rakesh. So capacity means how much, how it's a quantification measurement, right? Capacity means that ability, right? Yes, correct, Jyoti. So it's the ability or it's the capability of anything. So here, in terms of capacitance, we are talking about the electrical capacitance. What is electrical capacitance? So the electrical capacitance means the ability of any material to store electric charges. So my question is, what do you mean by capacitance? What do you think capacitance is, guys? Yes. So the capacitance means the capacitance is the capacity of a body to store the given charge. So it's the capacity of a body to store the charge for the given potential. Okay, this is the necessary condition. So the capacity or the capacitance means the capacity of the body to store the charges. Which type of charges? The electric charges. Okay, it's the capacity of a body to store the electric charges for the given potential. So these are the two conditions. Yes, correct, Madhavi. So these are the very important conditions. So capacitance means it's the capacity of body to store electric charges for the given condition. So it is given by, capacitance is given by capital C. So capital C is equals to Q by V, where Q is nothing but the charge stored in a body. Say if I have a body, how much charge can I store in that body? Say if I have, say a bowl. If I have a bowl, so this would be a body. Now, if I have some paper pieces, say if I have a paper, I'll tear that into tiny bits of pieces and I'll try to throw them inside this, or I'll just pour all the paper inside this bowl. So what is the capacity of this bowl to hold? Say if I have some 100 grams of paper pieces, if I have some 100 grams of paper pieces, and this bowl can store only 50 grams. Okay, what is the capacity of this bowl, guys? Say if I consider, yeah, the capacity of this bowl is only 50 grams, right? No, Hari Prasad. We'll come to generator later. Okay. So generator is not capacitance. So we'll come to generator. Okay. Okay, guys, come on. Say here we were taking the example of a bowl and a paper. Say if I have a bowl and if I have some paper bits, so these paper bits, if I consider them as electrons, if I consider these paper bits as electrons, then if this bowl is a body which can store only 50 grams of paper pieces, and if I have 100 grams of electrons, now what can you tell about the excuse me, capacitance of this body? What is the capacity of this body or capacitance of this body? It's just 50 grams, right? Yes. So its capacity to store these paper bits is only 50 grams. Similarly, if I have, say, if I want to talk in terms of capacitance, electric charges, say if I have a conductor, say if I have a spherical conductor and I have some positive charges, say I have a charge body filled with positive charges. Okay, say I have some 100 positive charges. I have some 100 positive charges. Okay, now I don't know what is this capacitance of this. I don't know what is the capacitance of this spherical conductor. Then I'll touch this. So there is some potential difference. Okay, so this is maintained at zero potential. So for conductance, we require two conditions. What was that? One is there should be a potential difference and there should be, yes, contact, right, for conductance. I hope you guys remember from your previous chapter. Now this is maintained at some 10 volts. Now when I touch this, what happens? Guys, tell me. When I touch this, everyone please try to answer. What happens when I touch this? Assume this is kept on an insulating shield, insulated table. Say this is kept on some plastic table away from the ground. Okay, this is kept on an insulated table away from the ground. Now I'm touching this charged body. Say I have a charged body of 100 electrons, which has some 10 volts. Now I touch this. Yes, how much would be transferred? Yes, there will be charge transfer, right? Yes, there will be charge transfer due to potential difference. That is, since this is, yes, there is charge transfer. How much charge would be transferred in this? How much charge would be transferred in this? Guys, come on, tell me. Yes, correct, Madhavi. Tell me in terms of electrons. Yes. Yes, correct, Dhanush. Correct, Rakesh. Awesome, guys. Awesome, you are. So, what happens when I touch this? Some 50 electrons diffuse in this. Some 50 electrons will flow to this. And how much voltage it would get? How much voltage it would get? It would get some 5 volts, right? So, when I touch this, to get some 50 electrons and it would get some 5 volts. So when there is abundance of electrons, should have some potential. Then what is the capacitance? Can you find what is the capacitance in this case, guys? What is the capacity of this, or what is the capacitance of this conductor only? So I remove this. I'll remove this conductor. Now what is the capacitance of this spherical conductor? Tell me. Yes, exactly. What is the capacitance of this spherical conductor now? Yes, 10. Okay, 10 units. So 10 units. For now, we don't know the units, so I am writing 10 units. Right, magnitude of capacitance is 10 units. Or, yep, correct, Dhanush, cool. Then, so I'll give you the units. The units of capacitance is then given as the SI unit of capacitance is farads. Okay, so I'll eliminate this units now. I'll replace this with farads. Okay, but guys, this is hypothetical. This is hypothetical. Okay, why am I telling hypothetical? I'll let you know. Okay, this is hypothetical value. Okay, this is not possible. Hypothetical means it's not possible. So yeah, so the SI unit of capacitance is given as farads. Any doubts in this, guys? So capacitance means how much a body can store the charge for the given potential. Then its SI unit is farads. That's what we learned from this slide. Any doubts in this? So the farad quantity, SI unit of the SI unit farad is given named after the renowned scientist Michael Faraday for his work in electromagnetism. Okay, we'll be learning about Michael Faraday more often in this chapter. Okay, so I told this is hypothetical. It's not real. Okay, this is not real. Why? So we'll learn why it is hypothetical. Okay. Now, guys, I have a similar question for you. So everyone, please try to answer this similar question. Yes, guys. So I have a similar question. Please try to answer. Yes, correct, Rakesh. So what is the voltage across the plates of a capacitor if its capacitance is 10 microfarad and the charge stored is 30 microcoulomb? So we know what was the expression for capacitance, guys? What was the expression for capacitance? C is equals to Q by V. Can you apply the value? I mean, apply the values, substitute the values, and find out what is my voltage. We are asking about voltage. What is my V? What is my potential difference or potential? Excuse me. Yes, many of you have given the right answer, guys. Come on, awesome. Jyoti, check your answer, please. Jyoti is, I mean, see, use also, guys. Please also use your SI units. I mean, convert everything into SI units. Okay. Correct, Madhavi. Correct, Santosh. Correct, Rakesh. So many students have given me right answer. Ramakrishna Reddy, correct? Come on, guys. Jyoti, check ಮಾಡಿ. Yes, Lakshmi, correct. So guys, come on, I'll try to answer. Okay, so please try to convert. See, this is just simple basics, just a substitution. So most of you had given me the right answer, that is option B. Okay, option B is the right answer, so this is right. So how, sir? Simply, sir, V is, see, if I know C is equals Q by B, then what is V? V is nothing but Q by C. So what is my Q? Q is 30 into 10 power minus 6, and C is 10 into 10 power minus 6. Okay. So 10 power minus 6, 10 power minus 6 cancels, 0, 0 cancels. I'll be remained with 3 volts. Okay. So option B is the right answer, guys. So yeah, you could expect, I mean, you can see that these questions, I mean, sometimes you may get such questions. Okay. Now, guys, come on, tell me, have you seen a battery, guys? Okay, everyone have seen and used a battery and are using a battery right now. Now I have a question. What is the difference between a battery and a capacitor? So guys, this should be an interactive session. Please try to interact. Okay. Please answer my questions. So what do you mean and what do you think the difference between, what is that one difference between a battery and a capacitor? Is there any difference? Is there any difference between a battery and a capacitor? Okay, yes. So Manohar says yes. Then others, guys, please come and tell me. Click on yes if you say yeah, there is a difference between a battery and a capacitor. Click on no if you say no, there is no difference. Click on yes. You have in participants. If you go to participants, you have in the participants you have yes and no button. If you say yes, please click on yes. If you say no, click on no, so that I can get the count of students who are telling yes and no in Zoom. In YouTube, guys, you could answer yes or no in the chat box. Okay. So far, okay, many of you say yes, there is a difference between a capacitor and a battery. Now, guys, okay, now tell me, okay, someone said no just now. I don't know why he, no, he left, I mean, he removed it. Okay, guys, cool. So now, if you say so, yes, there is a difference in battery and a potential. I mean, battery and a capacitor. What is the difference? Difference kya hai? Say if I have battery here, battery versus capacitor, capacitor. So tell me some differences. How battery is different from capacitor? Okay, Hamid give me general. Okay, we'll write the general terms of both. Okay, we'll write differences here and here. We'll write generalities here. Okay, so Hamid gave me one generality. So both battery and the capacitor stores charge. Both store charge. So this is one. Yeah, both stores charges or energy. Okay, given by Amit. So Purnima Nayak says, sir, capacitor is stored, I mean, capacitor stores energy or electric charges in the form of electric field, whereas battery stores electrical energy in the form of chemical energy. So Purnima, thank you. Yes, others guys, come on, tell me. So the difference is, yes, capacitors stores the electrical charge, electrical energy. Can I say electrical energy? Guys, is this visible? Whatever I'm writing, is it visible? Somebody please confirm, is this visible? Okay, cool. Thank you, Manohar. Ah, ಹೇಳಿ. So capacitor stores the electrical energy as electric field. Battery stores electrical energy as what? chemical energy. So chemical in chemical form. Okay, in chemical form. So I hope everyone knows. So what is that chemical form, guys? I don't know much of chemistry. Can you help me understand? Okay. Yes, Hari Prasad. So we'll come to that. Yeah. So Hari Prasad is asking, sir, if there is no difference, we would have used battery or capacitor in all cases. Acha, yes. Okay, come on. Suhas says the potential energy in capacitor is stored in an electric field, whereas in battery, the energy is stored in the form of chemical energy, right? So any other differences, guys? Any other differences? Guys, any other difference? Please try to be active. Try to answer. Any other difference? Okay, any other generalities? So do we have to charge both the capacitor and battery? My question is, should we charge a capacitor and a battery? Is it required, or do we get electrical energy as it is? Please tell me in sentence. Okay, answer me in sentence. So do we have to charge battery as well as capacitor, or does the capacitor or battery directly give electrical energy? So yes, guys, come on. We know for batteries, okay, there is one difference. For batteries, there are two types: rechargeable and use and throw. You know, guys, Gupta, for in batteries we have two types: rechargeable batteries and non-chargeable batteries. So use and throw batteries. So batteries which are rechargeable. So the similarities is rechargeable battery and capacitor needs to be charged. Okay, needs to be charged. Next, batteries enta. For batteries, some batteries which are non-rechargeable batteries, what they do? Non-rechargeable batteries, they just give out charges. Alva, provide electrical energy by changing from chemical energy, right? So in batteries, my chemical energy is converted into electrical energy, whereas in the case of rechargeable battery and in the case of capacitor, we have to provide some energy to that. Then it will store, I mean, the rechargeable batteries and capacitors, they store the electrical energy. So in case of capacitor, the electrical energy stored is electrical field. In case of batteries, the electrical energy stored as chemical reactions. So again, so yes, capacitor is a passive component. Okay, so this is new word. Is it a new word, guys? So guys, this is a new word for you. Capacitor is a passive component and battery is an active component. Okay, so I can't write here, I'll write here. So capacitor is an passive component, whereas battery is an active component. How many know what is passive component? Yes, correct, Suhas. Cool. So one more general difference. So passive component andre ಏನು ಗೊತ್ತಾ? So passive component is something which stores energy or consumes energy. Okay, passive component means stores energy or consumes energy. This is only definition of passive component. Okay, but capacitor just stores energy. Okay, whereas the battery generates electrical energy by changing chemical energies. Okay, so I hope everyone know your electrostatics, I mean electrochemistry might have been completed by now, at least in your CBSE. you might be knowing the redox reactions in which your transfer of electrons takes place, right? So you might be knowing Daniel cell, which is the chemical cell which gives electrical energy. Okay, okay, guys. So, okay, in capacitors there will be quick discharge. Quick discharge, and I know what is quick discharge, guys. Come on, tell me, guys. The difference between capacitor. So capacitor gives out quick discharge. So we have used capacitors. You know, how many of you know flash cameras? Before, okay, how many of you have DSLR or any other cameras? Guys, have you seen DSLR camera or any other cameras which has flash in it? Not the new ones, not the LED ones, but old ones. Yes, Manohar, any doubts? Manohar, you have raised your hand. Okay, you are telling yes, you have seen. Are you? Yes. Okay. I hope you might have seen DSLR or any other camera. So, in that camera, have you seen that flash? You have a flash, small flash in that. So, what is that flash do? What does that flash do? It will give out very high light at a short moment, right? How is that achieved? So in those flash cameras, they use very highly charged capacitors. Okay. So what happens? Those flash cameras just discharge the charges in charge iratala. Whatever the charge stored inside the capacitor, it's discharged in abruptly. The charge which are stored in the capacitor is discharged suddenly to create such flashes. So example is flash cameras. So capacitors are used in flash cameras, whereas in batteries they have very slow discharge. Okay, these are the difference between the capacitor and battery, and these are the similarities between the capacitor and the battery. Okay, guys, clear with this? Any doubts here? Any doubts here? Clear with this? Please click on S if you have any. Okay, please click on S if you are clear. If you have any doubts, please let me know. Click on no. Yes, guys, come on. Okay, thank you. So, okay, any doubt? So someone has doubt. What's their doubt? Please ask. If you have any doubts, please ask. Rajwal, any doubt? Rajwal, any doubt? Please ask me. Okay, cool. Okay, cool. Thank you, Rajwal. So next, so again, the difference between battery and a capacitor. Capacitors are similar to batteries because they store electrical energy. A battery can produce electrons, but a capacitor just stores them. Okay, this is the difference between a battery and a capacitor. So capacitor stores energy, stores electrons, whereas battery produces electrons. So if you want, it is more like, say, think of it like a water tower. Okay, you know water towers in your 11th, or say in dam construction, we have something called as water towers, or also in your schools. Say in your schools you have water towers. Say when they are distributing water, suppose there is excess amount of water, what happens? These excess amount of water, the school ಮೇಲ್ಗಡೆ ದೊಡ್ಡ ಟವರ್ ಒಂದು ವಾಟರ್ ಟ್ಯಾಂಕ್ ಇರುತ್ತೆ ನೋಡಿ ಸ್ಕೂಲ್ ಅಲ್ಲಿ. If you have seen in your school, there is a huge tank over right, over an tower. So there will be a tower like structure. On top of that structure there will be a tank, huge tank, which stores charges, which stores water. So whenever there is lots of water, what happens? Your water pumps will be storing those water. Excess of water will be stored in those tanks. Say when water is kali in your tanks, say when in your underground, when the water is low quantity, what happens? These excess waters which are stored in top tanks or tower tanks would flow to your houses. This is similar to that of a capacitor. Okay, similar. Next, guys. Now we'll discuss about the capacitance of a spherical capacitor. Yes, Rakesh, we'll discuss about fan capacitors. Those are called as condenser. We'll discuss about it later. Okay, we have that in our syllabus. That's a parallel plate capacitor. So in this case, we'll be discussing about the capacitance of a spherical conductor. So guys, tell me, can okay, let's consider. Okay, now can answer my question. Can my conductor behave as a capacitor? Guys, come on, answer this. Can my conductor behave as a capacitor? Everyone, please be active. Come on, guys, please try to answer. Can my conductor behave as a capacitor? Is my question. Yes, no, yes. So yes, many say yes. Yes. So we saw in our earlier example, in the case of conduction, say I had a conducting body, which when I touched the conducted body, charged body to this conducting body, this this conducting body got charged, right? Got charged and stored some charge. Yes, my conductor can behave as a capacitor. So we'll study how much can a what is the capacitance of a spherical conductor. Say if I have a spherical conductor, how much charge can that spherical conductor store? So to study that, let us consider a spherical conductor of radius r. So let Q be the charge on this spherical conductor. Okay. So we have a spherical conductor of radius r, and Q is the charge, total charge distributed over this conductor. Now, let V be the potential on the conductor. So it will be with respect to ground. If I take the potential with respect to ground, let us call its potential as V. Okay. Then, then the capacitance of this spherical conductor can be given as, so what is the expression we studied, guys? It's C is equals to Q by V. Now, can we apply this directly? Can we apply this directly? C is equals to Q by V. No, we know the value of Q. But what is the value of V? What is V? Do we know the value of V? Now, can we find the value of potential of any given charged body in free space using the electrostatics concepts, guys? So we studied this, right? We studied from electrostatics, we can calculate the potential of any given body. So the capacitance of the spherical conductor is given as C is equals to Q by V. Then the potential of spherical conductor. So guys, you remember in our last class, while deriving Gauss's law, or before that, we derived the expression for potential on the conductor, spherical conductor. Please try to recall that. What is the electric field? So we try to find what is the electric field on the conductor. What is the electric field, guys? So we know that electric field was given as E is equals to Q by 4 pi epsilon naught R square. So electric field of a spherical conductor was similar to that of point charge. Nene class al kaltidvi nenpidya. What is the electric field of a spherical conductor? It was similar to that of a point charge, that equates as kq by r square, right? Then what is electric potential? We know V is equals to E dot R. Guys, if you remember, V is equals to E dot R, we studied in our previous class. When we apply this, we get V is equals to E dot R, that is, we'll directly write the value of E, that is Q by 4 pi epsilon naught R square into R. Now what happens? R cancels, I'll get this expression. Okay. Where R is nothing but the radius. Yes, correct, Prajwal. Cool, superb. So then, what can we say about the capacitance, guys? Try to substitute this. Try to substitute the value of potential on this equation of capacitance. What do you get? What do we get? Yes, sorry, Prasad. Cool. Yes, we get C is equals to, the capacitance is then given as, what happens? So when we try to simplify, yes, the capacitance is given by C is equals to Q by 4 pi epsilon naught. What happens? Q cancels. I'll be left with 1 by 4 pi epsilon naught R. Then if I simplify that, then I'll get C is equals to 4 pi epsilon naught into R. So this is the capacitance of any given capacitor, any spherical capacitor or any spherical conductor. Okay, this is the capacitance of any spherical conductor, here the condition is it's only for the single body. Okay, here it's only for the single body, single conductor. Say if I have a single conductor, then its capacitance is C is equals to 4 pi epsilon naught R. Any doubts in this, guys? Yes, correct, Jyoti. Guys, any doubts in this? Any doubts in the derivation of capacitance of spherical conductor? Okay, no. So, guys, now I told you about capacitance unit. What is the SI unit of capacitance? Tell me. Okay, now, guys, come on, try to be active. Heli, heli. What is the SI unit of capacitance or capacitor? Farads. So, I told you when we calculated initially. So, you remember, guys, I told you 10 farads. So, the value of that in our initial example was 10 farads. I told it was hypothetical. You know why? So, you know, if from the expression, so from here, from this expression, now can you say what is the capacitance expression? So we know that the capacitance expression is C is equals to 4 pi epsilon naught R. From here, what can we say? From here, we can say the value of say 4 pi epsilon naught R is something like that. Say if I have the capacitance to be 1 farad, now if I want my capacitance to be 1 farad, then what should be the size of that conductor, guys? If I want my capacitance to be of 1 farad, what should be the size of this conductor? If we know C is equals to 4 pi epsilon naught R, then if I want a capacitance of 1 farad, yes, you guys said yes, the capacitance is derived in farads. Now, if I want the capacitance of the capacitor to be 1 farad, how much big radius or what should be the size of my spherical conductor? So we'll try to substitute that. Okay. Now C is equals to 4 pi epsilon naught R. Then C, if C is equals to 1 farad, that is nothing but 4 pi epsilon naught R. Then what should be my R? What should be my R from here? Yes, tell me what should be my R. So R can be equals to 1 by 4 pi epsilon naught, right? R can be 1 by 4 pi epsilon naught. From here, guys, try to rearrange. So I'll keep R here. I'll move 1 by 4 pi epsilon naught to the denominator of other side. So what I'll get? R value should be 1 by 4 pi epsilon naught. So what is its value? This is nothing but 9 into 10 power 9, if you remember. Yes. So if I want a capacitance of a capacitor of 1 farad, if I want a capacitance of 1 farad, I should have a spherical conductor. I should have a metallic spherical conductor of size 9 into 10 power 9 meters. Okay, here it's 9 into 10 power 9 meters. ಇಷ್ಟು ದೊಡ್ಡದು ಬೇಕು. If I want a capacitor of 1 farad, I need a radius of 9 into 10 power 9. 1 by k times. Madhuri? Oh, sorry, k times. Okay, correct. K times. K times is my size. So 1 farad is a very, very huge quantity. Then we can conclude. So my 1 farad is a very huge quantity. So my capacitance depends only on the geometrical properties of my conductor, and 1 farad is a very large quantity for the capacitance of a spherical conductor. So we can say that for capacitance of 1 farad, the radius is 1 by 4 pi epsilon, that is 9 to 10 power 9 meters. We need such big conductor. Is this big conductor possible? Can we get such very, very huge big conductors? Can we get such big conductors? Is it possible? So guys, now tell me, what do you think the size of earth could be? What can be the size of earth? Guys, you know what is the size of earth? What could be the radius of earth? Okay, come on, let's check. Okay, say, okay, any doubts in this slide, guys? Please let me know if you have any doubts. So for a capacitance, so farad is a very, very huge. So to summarize this, the capacitance is very, very huge quantity. The capacitance of any conductor depends only on its geometrical properties. And for a capacitance to be 1 farad, the size of the conductor of a single body should be of around 9 into 10 power 9 meters. Any doubts in this? Shall I proceed? Okay, no doubts. Cool. Thank you. Then, yeah. So farad, since my farad is very large quantities, we have to measure our capacitance in our day-to-day life in terms of picofarads, nanofarads, microfarads, and millifarads. Where pico is nothing but 10 power minus 12, nano is 10 power minus 9, and micro is 10 power minus 6, milli is 10 power minus 3. So all my capacitance will be in very, very small quantities. This is the reason why I said hypothetical condition when I started initially. Okay, next next over. So for this, what is the capacitance of single body? Say if I have a capacitance of this distance between earth and moon. So guys, now if I have the distance between earth and moon is somewhere around 384400. So that's not approximately, it's exactly 3,84,400 kilometers. If I have, assume I have a conductor of this size. Now, guys, tell me what could be the value of this size capacitor? Say if I have a capacitor of this size, say if I have a capacitor of this size, sorry, conductor of this size, whose radius is approximately 384,400 kilometers, then what could be its capacitance? ಇದರ capacitance ಎಷ್ಟಿರ್ಬೋದು? What could be its capacitance? Yes, correct, Rakesh. Capacitance depends on geometry and medium of surrounding. Maybe yes, Suhas. It's approximately 65,000. I mean 65 lakh meters or 6,500 kilometers. Yep. So if we take the ratio 1 upon 3840,400 kilometers, then its value is approximately, guys, if we have a capacitor of this size, a conductor of this size, whose radius is from here to here, say it would be having a capacitance of C is equals to 2.6014 into 10 power, okay, sorry, it should be 4 pi epsilon naught r, right? So it's 4 into pi into 8.854 into 10 power minus 12 into 384400. So this is approximately the capacitance of this size conductor would be 0.0427 farads. Okay. Yes, Prajwal, that's almost close. So its value would be somewhere around this. So ಇಷ್ಟು ದೊಡ್ಡ ಕೆಪಾಸಿಟರ್ ಇಷ್ಟು ದೊಡ್ಡ ಕಂಡಕ್ಟರ್ಗೆ ನನ್ನ ಕೆಪಾಸಿಟನ್ಸ್ ಇಷ್ಟೇ ಇರುತ್ತೆ. So for this huge conductor, my capacitance only will be this much. So imagine how large that 9 into 10 power 9 meters conductor would be. Maybe the Big Bang ball. So for earth size conductor, say if I have an earth size conductor, what could be its value? Say another earth size conductor ಇದೆ. Say if I have an earth size conductor, say the earth size conductor, say someone say it's like 6,500 kilometers might be the radius, then what could be its capacitance? What is the capacitance, guys? What do you think the capacitance would be? Say for the earth size conductor, so the capacitance will be somewhere around 700 picofarads. So for a conductor which is of earth size conductor, which is as big as earth, then for such conductors will be having a capacitance of approximately 700 microfarad. Then what about radius 1 centimeter? Say if we have a conductor of radius, spherical conductor of radius 1 centimeter, then its capacitance would be approximately 1 picofarad in order of picofarads. Okay. Yes, guys. Hello, guys. Any doubts in this? So my farads is very huge unit. So we can't use farads as and when we want. So farads na hingela use manakagala. It is a very huge quantity. Okay. Any doubts in this? Any doubts in these two slides? Earth size conductor and the previous. Yes. Okay. Shall I move forward? Guys, please respond. Response. Your responses must. I need your response. Please help me complete. Yes, come on. Thank you, guys. Okay, next, let's check. Okay, say how can I increase my capacitance? So I know if I have to increase my capacitance, I have to increase the size, right? Can I do it without increasing the size? My question is, if I want to increase the size, if I want to increase the capacitance, then I have to increase the size of the conductor, right? That's what we had studied now, till now. Now, can we use, can we use, can we find any other alternative methods if we can increase the capacitance without increasing the size? Can we do that? Please reply. Yes, no, you know, really. Yes, correct, Jyoti. Exactly. Jyoti, yes, it's superb. Others, guys, come on, YouTubers, try to answer. So how to increase the capacitance? You know, the capacitance is given by C is equals to Q by V. So if I want to increase my Q, I have to increase my area, right? I have to increase my size of my conductor, right? Now I can't increase my size of conductor. I have reduced materials available. Now, can I increase the capacitance without disturbing the size? Say I have a very small size conductor. So can I increase the capacitance without changing the size? Yes. So many are telling yes. Okay, correct, Bhargav. So that's one method. Yes. Yes, decreasing the potential. So how can we do that? So to do that, let me consider two conductors. Okay, let us consider instead of one conductor, let us consider two conductors. Say consider a conductor A of radius r and consider a conductor B of radius r. Now let us charge this conductor A with positive charges. Say let plus Q be the total net charge on A, and let's similarly charge the conductor B with negative charges, say of magnitude same magnitude Q but opposite sign. Okay. Now if we consider these two charges, then let VA and VB be the potential on these two conductors respectively. Okay, understood this? So we are considering two instead of one conductor. Now we are considering two conductors of radius r, same radius. One is charged with positive Q, other one is charged with negative Q. So let VA and VB the respective potentials. Now what happens? So guys, what is potential? What is potential? Can you tell me, guys, what is potential from our previous chapter? From our previous chapter knowledge, can you tell me what is my potential? Potential andre ಏನು? So the potential is defined as the amount of work done. So what was potential, guys? If you remember, potential is amount of work done in moving a unit positive charge from infinite distance to that point. Howda? Yes, correct. To a point r at the separation of small r or small d, right? Yes, exactly, Jyoti. So potential V is nothing but amount of external work done per unit charge. So this is what we learned in our previous chapter, right? So we'll apply that here. So let us again consider the single charge body. Say let's consider conductor A with radius r and plus Q charge. and VA. Now let us consider a test charge. So I hope you could see the test charge here. So I have a test charge Q. Now if I want to move this charge Q in this direction towards my conductor A, so what happens? What should I do? What should I do to move this charge? Guys, tell me, what should I do to move this charge? Yes, I have to do some work. So I have to do some external work. So I have to push this charge against the electric field generated, right? So this amount of work is stored as potential energy. Say I'll try to move this charge. Okay, I try to move this charge. I move the charge. Now this charge stores a potential of VA. Assume this charge is near to this. Now even this charge would be having a potential of V. I'll call it V. Okay, now this charge also stores a potential V. So what was the amount of work done? Let's consider W external is the amount of external work done. Now W external, we know that W external is equals to, sorry, W external per unit charge. External work done per unit charge is equals to V, right? My potential V is amount of external work done per unit charge. Now can I reduce by any way? Can I reduce this potential or amount of work done? Can I reduce this work done by any simpler method? Guys, really, can I reduce this external work done without much of stress? See, these both of these are positive point charges, so I have to do some work. Yes, I can introduce a negative charge here. So the potential at point A can given as C is equal to Q by VA is the capacitance of this single body. Now, when I introduce, say, instead of one charge, if instead of one conductor, if I have two conductors, if I have two conductors now, so I have VA and VB. Now, if I try to move this test charge, what will happen? What will happen? Now, if I try to move this test charge, what will happen? Guys, really? If I try to move this point charge now, yes, right? It's being attracted from infinity to this point. Yes, this charge is being attracted by B, and I need some extra force to push from here to here. So the external work done reduced, right? So there is a reduction in the external work done. So what happens? My V is equals to W external by Q. Since my external work done reduced, what happens? My net potential also reduced. Yes, it attracts. Correct, Hariprasad. So my external potential required also, I mean the external potential applied also or the potential net potential also reduced. So that net potential. So we can say C is equals to Q by V. My Q reduced. Sorry, my Q remains the same. My V reduced. What happens to C now? Iವಾಗ C ಏನಾಯ್ತು? My C increases. So this is one of the method to increase the capacitance. Say if I reduce the potential between the 2 point charges, say or between the two charged bodies, then the capacity of charge to be stored increases. The capacitance increases. So yes, the net potential at this point, at that point, reduces as V net is equal to VA minus VB. The net potential reduces. Reduce how much it will reduce? It will reduce by amount V net is equal to VA minus VB. Okay. Then the effective capacitance between these two conductors can given as Q C is equals to Q by VA minus VB, where Q is the magnitude of charge on any one of the conductors. So Q, Q is nothing but the magnitude of charge on any one of the conductors. So this is the effective capacitance of this conductors when we consider two conductors with one conductor having an opposite charge. By now, so what happens? C is equals to Q by V. We know the expression for capacitance. My voltage, the net potential difference reduced. So when my potential difference reduced by this relation, we can say my capacitance increases. Okay, understood, guys? Understood? So this is the way how we can increase the capacitance. So if you introduce two conductors instead of one conductor, if you introduce two conductors, then the capacitance or capacity of storing the charge increases. Okay. Yes. Cool. Any doubts here? Any doubts here? Any doubts till here? Any doubts so far? Please let me know. Yes. Cool. No doubts. So in general, we can define a capacitor as a device that stores electric charge. So what can we say that a capacitor is? A capacitor is any device that can store electric charges when electric potential is applied on it. It stores electric charges as electric fields. The capacitance of any capacitor is given as C is equals to Q by V, where Q is the charge on the capacitor and V is the potential difference across the capacitor. Okay, so guys, Aita. So this is much of capacitance and capacitor. Still here, guys, capacitance and capacitor. Understood still here? Understood till here? Please reply. Guys, I need your reply, please. Power bank is not capacitor. Power bank is a battery. It's a rechargeable battery. Okay, now power bank is a rechargeable battery. Okay, guys. Now I have a question. I have a question. So it's a fun fact. Answer this question. No, is capacitor a modern day device? Do you think capacitor is a modern day device? Are we using capacitor very recently after say colonization happened and revolution in the Roman Empire happened, Renaissance happened? So is it a modern day device? What do you think? Okay, no. So did our ancestors use capacitors? No. Yes or no? I mean, my question is, did our ancestors use capacitors? Don't know. Acha, don't know. It's a scalar, Rakesh. Potential is always a scalar quantity. It's a scalar. Yes. So, guys, no, capacitor is not a modern day device. Okay. So, capacitor is not a modern day device. So, we used capacitor in ancient times also. So, in ancient times, say in the early 18th century, in early 18th century, somewhere around 1735 to 1738 in Greece. Greece. Where is Greece? Guys, you have any idea where is Greece? Which empire is that? Greece. So it's the Roman Empire, I think, yeah, when Julius Caesar. So ಸ್ವಲ್ಪ history ತರ ಆಗುತ್ತೆ, don't worry. So it's the Roman Empire. So we have to know this, okay? This is important. I mean, not important from your exam point of view. It's just, yes, it's just an illustration which I'm trying to give. So this, which you see here, this image, this was considered to be a capacitor in our early 18th centuries. So they were using this capacitor. The modern day tasers, taser anta barat gotta? How many of you know tasers? How many of you know tasers? Any idea what is a taser is? I hope most of you might have seen in some American movies, I mean Western movies. No, I can't say in American. In Western movies, policemen try to use one gun-like structure which shoots out two electrodes, and this electrodes will stick to a human's body and gives electric shock. You know this. I mean, ನೋಡಿಲ್ಲ ಅಂದ್ರೆ ನೋಡಕ್ ಟ್ರೈ ಮಾಡಿ. If you try to check for tasers, okay, that those are tasers. Okay, so our early Roman empires. So okay, in early Roman empires, whenever they had wars, they were using this device as tasers. Actually, it was given somewhere, but I don't know. I'm not sure. But this device is called as a Leyden jar. So this device is named as Leyden jar. Leyden. Leyden jar. So they were using this device to store. Okay, Doraemon. So this is a Leyden jar. This was used in early 18th century, around some 1735 to 1738. So Leyden jar is nothing but its construction is similar to that of a modern day capacitor. So in some sites they had given the information that yes, they were used in wars as some emergency supply or something like that. So how is this constructed? Say I have a metal rod, so a non-conductive top, a metal rod, which is dipped inside, which is kept inside a cement. Okay, there will be an internal metal coating. So inside this, there will be some cement or mud, some non-conductor. Between this, there will be some non-conductor. In the outer layer, there will be in the inner layer, there will be some. Yes, this chain connects to this inner layer. So this inner layer is a metal coating. Okay, there is a metal coating here. Okay, in between this there will be some cement or any non-conductor placed in between this. Then the outer jar will be made out of again a conductor. So this was considered this was called as a Leyden jar. So why is it called a Leyden jar? This was an antique electrical component which stores high voltage electric charge, so between the electric conductors. So this was used to store the charge. It was found in somewhere around, it was expected or was discovered somewhere around 1745. Okay, so German scientists and the Dutch scientists found this. They discovered this actually. They discovered this in a city called Leyden. So they discovered this jar in a city called Leyden. So this is called as a Leyden jar. So this was capacitor. We can say this is an ancient capacitor. So this was the very first capacitor known. So modern days capacitor is something different. Okay. So with this, we'll end our class today, guys. I'm launching one feedback to all of you. Please take this feedback, give feedback to me if you find, hope you like the class. Okay. Now, in tomorrow's class, we'll study about the parallel plate capacitor, construction, and working of parallel plate capacitor. Okay. Yes, it was invented before. They discovered it. So it was invented. I mean, it was discovered in 1745, Hari Prasad, but I think it was invented way beyond before that. Okay. So this Leyden jar, if you want more details, you could check on internet. So this is one fun fact. Okay. So in today's class, we learned about capacitor, capacitance. What is a capacitor? What is the basic construction of a capacitor? I mean, what is capacitance? Capacitance means a device which stores charge in it in the form of electrical fields. So we learned about a spherical conductor. Yes, a spherical conductor can behave as a capacitor. So we checked what is the capacitance of a spherical conductor, and we also checked the condition that the capacitance depends only on what? Only on geometrical properties. That is very important. The capacitor depends only on the geometrical properties. Okay. And we studied about the expression for capacitance. Then, yes, we found that the capacitance of earth size conductor and beyond earth size conductor, and we note that we came to know that farad is very huge unit. Say for a capacitor of 1 farad, it should be having a very huge structure of conductor. Say for an earth size conductor, the capacitance was approximately around 750 microfarads. And we also checked for uh, the capacitance of how to increase the capacitor. how to increase the capacitance. So we used two characters instead of one. Then we could find that there was increased capacitance by decreasing the potential. So this was much of it. In next class, we'll be learning about the capacitance of, we'll be learning about the next concept is parallel plate capacitor. We'll be learning that. Okay. We'll be learning the parallel plate capacitor in the next class. Yes, till then, please come prepared to the next class. We will be discussing about parallel plate capacitor and stuff. Okay, guys. So everyone, please give a reply to the polls and then leave. Okay. So any doubts, guys? You could ask any doubts if you have. People who have doubts can ask your doubts in the chat box. Yes, guys, please try to ask your doubts in the chat box if you have any. Okay, I'm waiting. So guys, everyone please try to give your polls. Everyone please try to give the poll, respond to the poll. And if you have any doubts, please ask me. Okay, Rakesh asks, so capacitance depend on charge of conductor and potential of conductor. Rakesh, no. Please check that. So we know the expression for capacitance is C is equal to Q by V, right? I didn't get your question, Rakesh. Are you asking capacitance doesn't depend on charge of conductor and potential of conductor? What do you mean by this? So the capacitance of a conductor depends on the charge stored on the conductor. So how much charge it can store for the given potential. I think that's the proper explanation for your doubt. So how much potential we give and how much charge it stores based on the potential. So that can be given as the ratio of charge to potential can be given as the capacitance. Okay. Okay, guys, please, everyone in Zoom, please give your feedback in the teachers NPS. Please click on if you have any doubts, please ask, and you can leave if you don't have any doubts. So any more doubts, guys? Please let me know if you have any doubts. No, it doesn't depend on that, Rakesh. Yes, it doesn't depend on charge. It depends only on how much. Yes, thank you, Kiran. So it depends only on how much potential is applied on it. Okay, how much is applied, and based on the potential applied, how much is it able to store the amount of charge. So how much of charge it can store. So that is the basic definition of capacitance. Okay. Okay, guys, cool. Then we'll meet again in tomorrow's class. For yeah, we'll meet again in tomorrow's class. Please come prepared with the parallel plate capacitor. We'll try to solve some problems. Where, Rakesh? For a test charge, yes, we assume there exists Any other doubts, guys? If there's no doubts, we can wind up. So I'll wait for some time. Any other doubts, please ask me. If you have no doubts, you can leave the class. Okay, guys, then we'll see again on tomorrow's